keep it over there. Yeah, good.
Something.
How much?
Yeah, that's enough.
Good. Change that caption. One more. Thank you very much. Thank you. Oh, you get the picture.
Sucking urine.
Welcome. Burroughs Welcome got an early drug of theirs was liver extract, which was lots of neat things. But in addition to that, it's got some very important biochemistry that is photosensitive, and that's illustrated by this slide. Bacteria use the carotenoids to protect them from the sun when it's sunny, but they don't want to make them if it's a monomer, and that monomer falls off at a very short time, so in about 150 femtoseconds. And different change platform for photophysical studies because they have these two different transitions with two nearly perpendicular transitions.
Instead of doing this experiment at Fermi, but still at Fermi we cannot cover the same population of the states lifetime. Still, basically there are two lying the blue lake excited state is dynamic
different signal. It won't necessarily affect the shape of the different signal. Yeah.
And so I'm taking a very conservative approach.
Mhm.
Let's say the normalization is off by 2%.
I was looking at the one that I need to go to that. And bring that to there. That's and that clearly.
Well, that really makes that look like a new feature.
And that makes that look like a new feature at the early times. And this would be the worst.
What is the...
What we saw instead from the X-ray emissions, another data from 2020, is that in fact it's X-ray absorption, X-ray emissions on the next one. The X-ray absorption shows very similar behavior for the aqua and the high.
Pre-age structure. This is the one as D transitions.
Yes.
As far as I understand, this is because of quadrupole transitions. Do you account for these transitions in the interpretation of your data?
Yes.
Only for
They're very.
My name is Jim Pennerhan. I'm a professor of chemistry and biophysics at the University of Michigan. And we're here at the European XFEL because we can make measurements on X-ray emission of dilute samples that we can't make anyplace else in the world. What we're looking at is vitamin B12, so-called cobalamin. We're trying to understand what happens in the very shortest times between excitation and eventual relaxation. This is a joint project between my group and Professor Senshin, also at the University of Michigan. Professor Senshin's an expert on ultrafast. My background is in X-rays, and we've found that our collaboration allows us to ask and to answer questions that nobody else has been able to explore in this domain. The European XFEL lets us make measurements that we can't make anyplace else. It has a higher intensity and a setup that allows these very dilute solutions to be studied that we've not been able to make this kind of measurement anyplace else.
Okay, I'm Professor Senshin at the University of Michigan, and we've been working on ultrafast X-ray experiments for about 7 years now, and have been really excited to be able to come to the European XFEL to do these X-ray emission measurements, because it gives us the opportunity to probe our molecular systems from a different point of view, looking at very dilute samples and very weak signals. And so that's something that extends our understanding of these systems enormously.
I'm Ryan Lamb. I'm from the University of Michigan. I'm a graduate student. I'm glad to be here at the European XFEL. We're collecting a lot of interesting data, and it's a very fun and somewhat groundbreaking experiment. The European XFEL is a great facility. It's comparable to LCLS in California. We've had amazing beam time with the X-ray beam not dropping very often or at all since we've been here, and so that's been really great.
Hello, my name is Ailey McLean. I am a graduate student at the University of Michigan, and I'm here at the European XFEL on my first international beam time. Pretty exciting. Fortunately, I do have a cold, which isn't as exciting, but it still hasn't really detracted from the experience. I'm really excited because we're studying a molecule that's really important to my dissertation research, and so I'm really excited to put that in a beam and see what happens to it. And I like the atmosphere here. Everyone is very open and willing to communicate with you about ways to keep track of what's going on, so I do like the communication here.
Oh, hi. This is Aniruddha Deb from University of Michigan and from the Department of Chemistry. So I work with Jim Pennerhan at the Department of Chemistry. We are here to do X-ray emission studies with a set of cobalamines, and these are very dilute samples which can really be done in any other facility except the European XFEL. So this is a unique facility which is available here, and that's for the reason that we came over here to do these set of experiments. We did another set of experiments. Unfortunately, those were remote set during the COVID. So this is the first time we have been able to come in person to do these experiments out at European XFEL.
Yes, exactly.
We just want to find best positions. The VFM is pretty flat. So we first scan HFM.
One left. So it's worse.
Let's wait just a second. Let's wait a second.
No, I think the same.
So this was a 2 centimeter step.
Yeah.
Makes sense. That's what we figured out from our scan.
I mean, but I would like to see this at some point go down, right? So should we take a very large step? Yeah.
Okay, I mean, just not down, it's just flat line.
Couple of meters. It should be fine. It should be fine.
Here we are. Oh,
yeah. Yes.
Oh wait, okay, now I go between the two targets.
Are these the integrated signals up there or just the maximum?
It's the integrated signal
of the whole chip.
around
Yeah. What was running?
New scan.
100? A new scan.
In this position, and then
100 is garbage.
No, it's just they take a.
It's
just around.
static around.
Wave functions is what they look like. The good thing you have, exactly, because these can be terribly low because we have a very.
If we look at the valence photoelectron spectrum,
very
very
localized wave function.
Well, I think I don't need to talk about European Maxwell facility because it's very well known that it's unique and it's producing high repetition rate pulses, very short pulses. It's brilliant and energy range. I mean, it's really great. But I have some personal feeling to come here, and because I like the people who stays here, who works here. They are my colleagues, they are my friends, they are my best friends. We know each other like 20 years. We spent the life together, we build our career together, and it's always great to come and hug them, to be with them, to take a coffee with them, to discuss our problems, our life, our families, and just this is what I think is from my side, it's the best all the time to come back and stay here. Of course, environment is something, it's awful. You feel like at home. Come on, even if you are doing the night shift or you're working 24 hours per day.
The European XFEL is a facility in which people which are interested in photochemistry, like I am, can find very peculiar characteristics. For instance, here it's a source of X-rays, so this means that one can interrogate the atoms in a molecule in a very specific way and understand the role of each atoms, like carbon, oxygen, or nitrogen in a specific compound. And also it provides very short light bursts which act as the shutter of a fast camera, so that one can follow the dynamics in a photochemical process, so understanding what's going on, for instance, during a chemical reaction. And this is extremely interesting. Besides that, it's very nice to come to the XFEL for doing experiments, because there is a nice community of high talented scientists and friends that we meet every time we come for a bin time.
So we're coming to the European XFEL because we can do our science with the fantastic people here from the SQS team. The topic that we're investigating is actually the photoprotection of nucleobases. Nucleobases are an integral part of our body. They're inside our genetic code, and they have a super strong UV excitation cross-section, which is absurd. You ask yourself why nature has this precious molecule with strong UV absorption cross-section in our body. Yeah? And we're investigating here the internal photoprotection mechanisms of this nucleobase. For that, we're using the high-energy soft X-rays to do core-level spectroscopy on a couple of atoms inside the nucleobase, and we can really here watch how the molecule protects itself from the UV radiation, and how in this process of the protection the charge moves over the molecular body with really high precision, both in space and in time. So to say, we make a movie of the charge moving inside the molecule. So we're here at SQS, we're using a photon energy of 600 eV, which is really special. We have a good temporal resolution in the regime of probably better than 50 femtoseconds, which is ideal for actually investigating the processes in this molecule.
When you do a second part, then it will override. Can you simply do it back now? Because I think ILM. Yeah. Because it switches. Okay, that's an error which I have to solve. That it finish with that before jumping to the next.
But it's not going to back right now.
Huh?
It's not moving right now.
The slider attenuator is
Yes.
in.
So we can
Okay, I trigger a main shot.
You are currently in the position that is undefined. It is, however, probably only Z that is off. Z went to parking.
Shall we park it anyway, or do you need it for another place? You know, so we have finished with all the lines you wanted to do?
Yeah, we just aligned the two samples. Yeah, yes, I. Not for ILM.
Do you want to have a post shot?
Okay, that's good. Did you close the Festo shutter?
Normally not, but I moved properly in the ILM.
With this background to compare with you. Oh, sorry. So you now have this later.
Okay.
Yeah, because yesterday we didn't
But this
say
is
that.
caused by because like we can't close the slit. That's it.
We think.
Well,
If we close the slits, then this facility
be
becomes
pretty sure
stronger,
because
but
like
that might
when
be.
Michael starts to.
So yeah, that looks all fine. So we could now move back to the edge, really.
You do it a D-scan or you do an A-scan on this?
Wait a moment. D-scan.
Okay.
What is the direction? Keep the backlight on. And do the next scan in the opposite direction. Okay, let's stop this.
Okay, my name is Lingan Huang, so I work for Helmholtz and Thun Dresden-Hossendorf. I came to HED on this Monday. I work here many experiments, and this is my first leading experiment. I was quite excited about it, and we try to understand the plasma physics. That's why we need X-ray to probe what's happening inside the material, inside solid density plasmas. And this facility is quite unique that we can bring the experts from different fields to work together. I was also in art facilities like in Sakura in Japan, and this environment is feels quite international for me, and that we can do very interesting physics here. And the experiment is running already for 1 day. It looks quite successful, and we are expecting to get rich data we can analyze later. And we feel very exciting to work with the SFL facilities.
Hello everyone. I'm a PhD student working in the ICDR, and I'm working in the theory of laser plasma interactions. So today I come here for a real experiment of laser plasma interactions, and X-FAIR have a very unique feature that can detect a very short-time physical process in the laser plasma interactions, and this experiment can verify the theoretical parts of the physics. So it's a very nice tool to benchmark the theories.
Hello, my name is Lisa and I'm postdoc at the University of Siegen, and I'm working on the surface dynamics of laser irradiated solids using the free electron laser to investigate the surface dynamics in nanometer spatial and picosecond time resolution. And here the X-FAIR with the group around is a great opportunity to really get insights into the first nanometers of a surface.
Hello, I'm Maddalena Bin from Stockholm University, and I'm here at MID to perform experiments on proteins. So what's special about European XFEL is that we have megahertz repetition rate. That's allow us to study the dynamics of protein systems in very fast timescales, like sub-milliseconds. So then we are here, we are very excited about the results. We already had a nice signal. That's wonderful. I don't know.
Hi, I'm Christian Gott from the University of Siegen. We are interested in the dynamics of protein systems, Here at the European XFEL we find the best conditions to make molecular movies. We make use of the high repetition rate and the high coherence of the European XFEL and follow the motion of the molecules in real time.
Hello, my name is Filip Meyer and I come to the European XFEL from Uppsala in Sweden to carry out my experiments. The European XFEL is able to provide me with the extremely bright X-rays that are needed for my experiments, and with them I am able to image single viruses and tiny samples like single proteins. And with the help of the staff at the European XFEL we are able to make those experiments a success.
Hi, I'm Patrick Adams. I'm a PhD student from RMIT University in Melbourne, Australia. Today at this experiment we're looking at bacteriophytochromes with the pump probe laser. Particularly my work's in the correlation analysis aspect of that, so we're looking at the X-ray scattering and measuring correlations within each of the pulses and trains. It's really exciting to work here at the European XFEL. I've really enjoyed the international collaborations and the research that everyone's doing here.